Oh, that's wrong. Okay, so there we go. So kind of the part of the paper that I wanted to focus on is this idea of multimodal generation, because that's a lot of what we had to focus on to get a method that was performant. But first, like, what is multimodal generation? So there's this term is actually used in a couple of contexts. One context for multimodal generation is that when the generative distribution we're learning has multiple modes. So like it could be like there's one area, like most of the examples are concentrated around a certain main example, or it might be that there might be two canonical examples or many. So that's one example of multimodal generation, but that's not actually well, actually, the distribution we had to learn in this paper was multimodal, but I really want to focus more on multimodal in terms of data modalities. So in this paper, we were going from text to graph. So the input and the output of the generative model are different modalities. Besides that type of multimodal generation where the input and output are different, another case that you often fall into with multimodal generation is when you have multiple different input modalities. And actually, this work falls into that category too in a way that I'll show you later. And that's kind of what I want to focus on. It's like, how did we deal with multiple different input modalities in our model? But before going there, I wanted to talk to you about like, why is multimodal generation an important problem? So different modalities describe different information about a concept. So like an image of an object can provide information about it, like its color, scale, or material, but its taste can also provide information about its chemical composition or nutritional properties. So like you can tell something a lot different about an apple by biting it than by looking at it. But it also can help provide information like to disambiguate things. So when you see apple in text, you don't know if they're talking about the company or the fruit. So really including different modalities, what it can allow you to do is just include different types of information about the same concept that you want to perform inference on. Okay, I've introduced this. Oh, okay, so and to give some like concreteness to the actual work that we're working on, where we're going from text to graph. Some of the applications for this type of work is you could improve software development, because this is something I learned when I started looking into this. But one interesting thing is that a lot of like compilers, what they do is they actually treat the functions that you write as trees. So you can translate your code into what's called like an abstract syntax tree. So for example, and that's a much more easily compilable representation of code than the abstract text, than just like raw text. So for example, you could learn to go from docstring to abstract syntax tree, which could improve software development by just making it a lot easier to develop the types of functions that you're looking for. It could improve drug discovery by going from like functional requirements of molecules to molecules, and that's kind of the experiments that we did here. Or the real use case that we're trying to, well, one of the use cases that we're working on at NPlan is that it could improve project management by going from like a description of a project to an actual project schedule. Okay, so before I said that we're going from text to graph, but actually what we're doing because of the approach we took is we're going from text and partial graph to partial graph. So a lot of this work was figuring out how to marry these two representations together. Oh yeah, cool. But before going down that route, I wanted to talk to you all about like what defines a data modality, because we're talking about multimodal generation, but what makes something a data modality? So one thing is that there's shared structure between all of the elements in that modality. So for example, with images are basically, I think, almost exclusively represented as grids of features. And so that's a shared structure because you know all of your features can be represented within a grid. The other common element of a data modality is that there's often some kind of invariance or equivariance relationship that exists for all points in the modality when you're performing inference on them. So I'll tell you what, come back to this, but so what is an equivariance and invariance? I've had to remind myself of this definition so many times. But so first let's talk about invariance. So G is some kind of transformation. So for an image, it might be like rotating the picture of the dog. And what this is saying over here, this equation is saying, so like if you perform the transformation on the image, you should still get the same output for your function. So you want a classifier, for example, that's invariant to like rotating the picture because there's still a dog in the picture even if you rotate it. So that's what invariant means. It means that the output will always be the same despite the transformation that you might apply. And then equivariant means that it doesn't matter when you apply the transformation. So for example, you might be doing some kind of superpixelation, which means that you take an image and you expand it and then you fill in all the pixels. And you could think of like, okay, if I rotate it and then do the superpixelation, then it should be the same as if I do the superpixelation and then I rotate it. So one is like the output is usually like a single number, and one is just a transformation of the image itself or the modality itself. But so there's these like equivariant and invariant structure relationships in the data. And for images, there's actually quite a few. Like ideally, we want a model that's scale invariant. So it doesn't matter how big or small the object is in the image. Rotation invariant, a lot of the times like even changing the color of it. And these are all like really common data augmentation techniques because these are invariances we want in the in the model for computer vision. I went through this. So these invariances are often encoded into the models we use to process a specific data modality. And this is like the term for this. This is an inductive bias we introduce into the model. So for example, convolutional neural networks, which are part of state-of-the-art for computer vision, they're much more translation invariant than MLPs. I don't think they're completely translation invariant, but they're near there. So that means that like you can move an object around an image and it can still be identified by the model. So that's a form of invariance in the model. Yeah, and the reason why introducing these inductive variances are so useful is because they simplify the learning problem. It means that your model can only learn features which also contain these invariances. Instead, what would have to happen is that you'd have to throw so much data at it that the model would learn how to distinguish, like this invariance doesn't matter. So it makes the models like much more data efficient and just like more effective. Sometimes you can't even learn the invariances that you would like to learn. So state-of-the-art models for different modalities are like for text and sound, it's transformers, which basically treat these types of data as sequences. For images and point clouds, it's CNNs. And for graphs, it's graph neural networks, which is something we use a lot at NPLAN. But there's exceptions to all of these, actually, if you look in the literature. But these are kind of like the canonical, or the main models used. So I wanted to look at the two modalities that we are working with in this paper, which are text and graph, and talk about those specifically. So what's the structure in text that you're trying to like take advantage of or maintain? For text, it's that text is a sequence and that elements in the text cannot be reordered and represent the same concept. I'm sure we can come up with like some kind of exception to this rule, but like broad strokes, you can't reorder words and get the same sentence. So I just like reordered the nouns in this sentence, and you can see it like means something completely different. Sorry. Okay. And so what inductive bias is introduced into models to that process text to deal with this structure, like that text sequences are ordered? Well, in transformers, we add position embeddings to treat the text as a sequence. I don't know and funny enough, I don't know if you guys know this, but if you didn't have the position embeddings, then transformers are basically order invariant. They don't care what the sequence order is. So you add these in, and you get your. This is how you enforce the ordering in a sequence. So they're like hidden features you don't even know about unless you look into them, but they're super important. And so how about graphs? So what is a structure in graphs? I always go back to the definition where graphs are a set of nodes and a set of pairwise relationships between nodes. And that means if you change the set of nodes or the set of edges, the graph is not the same. So if you move this edge so it was here, you wouldn't have the same graph. But if you change the ordering of the nodes or the ordering of the edges in the graph, it's still the same graph. Why does this even come up? Because when you express a graph in a computer, it has to have an ordering for the nodes, because you have a list there that you're using to perform a lot of like matrix operations and stuff on. Models processing graphs should be invariant and equivariant to node ordering and edge ordering. So that's the kind of I would call it the structure of the modality that you want to enforce. And so I just wanted to show you guys how this is done. So I might stay on this slide for a long time. So what's the inductive bias in models that are used to process graphs? So graph neural networks pass messages locally such that information transfers between nodes in a way that node ordering and it's node ordering, edge ordering invariant. So let's say this is a graph here where these lines define the connection between the graph. And this is like a representation of the adjacency matrix, which is like a representation of these edges. With one exception, which is that this matrix has a self connection. So node 1 is connected to node 1, even though there's no like self loop here. But you can see like node 1 is connected to node 3. So you can see node 1, node 3, they're connected. Or node 1 is connected to node 8, so they're also connected. So this adjacency matrix with the augmentation of the self loop actually expresses how graph neural networks work really succinctly. What would happen is like at each layer, say you had node 1 and you wanted to process it in a graph neural network. What would happen is that this node would have some kind of feature representation, and then node 3 would have one and node 8 would have one. And basically what would happen is that the model would take node 1, node 3, and node 8's representations and collect them all together and aggregate them in some way. If you wanted to be really similar to transformers, you could use a graph attention layer, which actually weights how much you should take into account node 1, node 3, and node 8. There's other ones that just add them all together. Well, it takes the mean of all of these three. So, but by doing this local operation, so for each node 1, you're only taking into account the local, the nodes near it. It actually makes the operation of calculating a new representation for the graph node order invariant, and then it's edge order invariant because you're not even ordering the edges in this case. But so that's kind of how message passing works. That's the main operation within GNNs. And that's how we introduce that inductive bias of being node ordering and edge ordering invariant. Okay, so that's a little bit of an introduction into like the two types of data modalities that we were using in the work. But let's talk a little bit about how we combine them. So we decided in this work to represent graphs as text. And here you can see like a made-up molecule. And the process of going from a molecule to graph to a text representation, we called it a serialization. And you can see, I'll just explain the serialization so you get an idea of what's going on here. So each edge in the graph is described individually. You can see there's 1, 2, 3, 4 edges. And the syntax is as follows. You add some kind of special token to indicate like your predecessor node. Then you have your feature string for that node. So like your carbon atom. And then you have another special token to describe your edge. And you have like your feature string for your edge. And then you have another special token to describe your successor node. And then that node's feature string. So in the case of this work, all of the the graphs we were using, they were text, like the features were text-based, but most features can be converted to text, so I don't think that's very limiting. So that's the syntax. So what you would basically do is order your edges, and then use this syntax to serialize them into a single string. There's one final nuance, which is that, like in this molecule here, I should have taken these 0, 1, 2 away, but there's actually 3 carbon atoms. So you have 3 atoms that all have the same feature string, which is just a C. And to distinguish them when you're serializing them, because if you don't, then you can't deserialize them, we do something really simple, which is just like add another token and an integer to describe that they're different. But anyway, I feel like it's the simplest algorithm that you can come up with for serializing a graph. And when we were doing experiments, I actually started with something a lot more complex, because I was starting off of, if any of you guys have heard of this before, in chemistry, there's something called the Smiles algorithm, which is a way of describing a molecule as a string, but it uses, like, in my opinion, a much more complex serialization method. This is much simpler. And simple seems better for LLMs, if anyone's interested in that. So anyway, we decided to represent graphs as text. And we did that for 2 reasons. One, it allowed us to jointly process additional information. So you can have a single model taking into account that this is the request of the molecule that you want, and then this is the molecule that you're trying to generate. And then 2, so it's going back to like how you can, this text is describing the molecule in a different way than the graph does. But by representing the graph as text, you're able actually to take that information into account. And then 2, just like state-of-the-art we could use state-of-the-art text generation models to generate graphs. Because if you look into the graph generation literature, actually one of the limitations, at least that I noticed when I was doing a literature review, which may have changed now, was that there's not a lot of literature on generating really large graphs. But there is a lot of literature on generating really large sequences. And at NPlan, the sequences that we're dealing with the programs that we're dealing with, are massive. Like, I've seen programs that are 150 or 200,000 tokens in length, which is just a really long sequence. And so but we were just trying to take advantage of like models that were able to generate large sequences by going down this route. But there was a difficulty there, which is that state-of-the-art text generation models are fine-tuned, pre-trained large transformers, unless you can do some kind of in-context learning. But these models model their generative distribution as autoregressive. So what does that mean? Say that you were trying to generate an entire sequence of text, which was composed of 4 tokens. The way that it would work under the hood is that you generate the first token, and then you condition your next token off of that generation. So you get at the first token, then you generate the second token, and you condition off of these 2 to get the third, and you condition off of these 3 to get the fourth. What that means is that you're always taking into account everything that's happened before in order to get the next token. It's actually quite a slow process, but it's really good at generating text, and that's why it's so performant. But what it does introduce is, when you're using an autoregressive model, there's a difference at training time versus generation time. So at training time, your model is going to see all of this sentence, and you're hopefully going to learn to generate all of this sentence. But at generation time, like we talked about before, you're going to start with the first token and generate the second, and then you're going to take the first 2 and generate the third, and so on. But what that means is that there's a difference between training time and generation time because of this autoregressive generation. And what that means is that at training time, you need to make sure that you're not passing information backwards in the sequence, because when you're generating, you can only see up to the point that you've generated, but nothing afterwards. But transformers don't naturally have a way of stopping information from being passed back in the sequence. they see the whole sequence at the same time. So what we do in practice is we do something called causal masking, which is where you might have a sequence like the one here, and when you're training the model, you don't have to do this at generation time. You instead of just so everyone knows, the way that transformers work under the hood, like the main operation that they perform is attention, and it's kind of like the message passing we saw with graphs before, in the sense that you take into account other tokens representations and you come up with a new representation for each token. And so like if you were token 4 in a transformer without causal masking, it would take all of the other tokens representations and that token's representation and aggregate them in some way to get a new representation for token 4. But with causal masking, instead, it just takes all of the ones beforehand. And that's how the model learns to generate, even though at training time, it's seeing the full sequence that it's trying to generate. So that's an important element of how we train autoregressive models to generate sequences of text. So when we're trying to combine models for processing these two modalities, you have on the text side, and using a text-based model, information cannot be passed back in the sequence. Models only pass information forward. And then when you're looking at graphs, node ordering doesn't matter, edge ordering doesn't matter. Information passing is agnostic to sequence order. So you actually have these two things that are, one doesn't care about order and doesn't know about order, and the other one does know about order and really cares about it. That was kind of like one of the technical problems that we solved in this paper. Moving on to how we kind of solve that problem is, so we're combining two modalities describing the same concept. And so ideally, we want a model processing multiple modalities. The model processing multiple modalities should be able to share information between modalities during processing. And this is to take advantage of information only available in the other modality. So like I said, here we have these molecules that are represented as graphs, and then it's these sequences of text like serialized graphs. And what we did in the paper is we took like any standard LLM. Let me just take a second. Any standard LLM, and so these blue layers are just pre-trained LLM layers, and we put message passing layers in between them. But we still have to, I haven't told you, I'll now talk to you guys about how we solve this problem of dealing with these two different types of models. And so the message passing layers must not pass information backwards in the sequence, otherwise the model will not learn to generate graphs. So that was the rule we had to figure out how to overcome. So within these message passing layers, we perform what we call causal graph attention, which is super simple. I think through this diagram here. So we have this again, these nodes. This is the graph, and then this is if you just represented them as a sequence. And so if we were just doing causal masking on them, this is what the adjacency matrix or the matrix would look like for the masking. If we were doing graph message passing, that's what it would look like here. And so we did causal graph, which is just combining these two, doing an element-wise product. And that's what's happening within the message passing layers. And what it does is that it ensures that even though you have message passing layers between these LLM layers, you're never actually passing information backwards in the sequence. And in turn, what this allows us to do is view this sequence of text both as a graph and as a sequence of text at the same time within the model. So yeah, there's actually more components to the paper than this in terms of the methodology, but I wanted to focus on just that one. And I hope I explained it in a way that is understandable. And now I'll just move on to like the experiments and the results real quickly, and then we'll get some questions in. So another interesting element of this paper is the fact that, so the prior work into like text-to-text graph generation focused on the case where you have some kind of paragraph and you want to pick out the knowledge graph that's described by that paragraph. But what that meant is that the paragraph, it describes exactly the graph that you're trying to generate. Like it will say the edges, because the knowledge graph, it describes relationships. So for example, it might say Barack Obama is the president of the United States, and that means that you should have Barack Obama and president of the United States connected in the graph. And what that means is that for every single example in your data set, there's one graph that corresponds to it. But when you're doing conditioning off of functional descriptions, for example, you say like, I want a molecule that has 23 valence electrons. Then you actually have many, many molecules that could correspond to that. And in that case, you kind of need like a completely different way of evaluating or like your methods, because you can't just say like, is this graph the same as the one that I have for this example? So what we did is we got this massive data set of molecules that's just publicly available online. And then we combined it with this Python kit called RDKit. And RDKit, what it can do is it can actually calculate a lot of functional properties of molecules. So like the number of valency electrons, or there's this one that I think is like a little bit more sexy to people in molecule generation called quantitative estimation of drug likeness, which is like a quantitative metric of how how many nice properties for making drugs does a molecule have. But in each of these cases, what's cool is that you can generate an entirely new molecule, feed it through this Python kit, and get this number, like the number that's the functional property that you're looking for. And so we created these two data sets, one with valency electrons, like the number of valency electrons, and one with quantitative estimation of drug likeness. And we trained a model to generate molecules based on those properties. Yeah. And here are some of the results. These are two baselines that I didn't want to go into because I didn't want to talk too much about everything in the paper. But so we have our model. We actually introduced like a new training objective with it as well. And that's what this one is. So we have like a couple of variants of our model without message passing, and then with two different types of message passing. So incorporating those layers that we were talking about. And you can see the performance of the model in terms of mean absolute error. So that would be like the difference between the requested functional property and then the one that you actually got off of it. And so for example, for quantitative estimated drug likeness, the model with edge message passing, it has a mean absolute error on average of 0.036. This table on top is really important to being able to understand these results, because you can see that like for the data set that we were evaluating on, the standard deviation is 0.11133. So this number is like 4 times less than the standard deviation, which shows that the model is actually learning something. Because if your model was just basically, if the mean absolute error was this, it means that you could basically randomly guess from the data set and you would get a similar result. There were some other metrics that we used as well, like how often it generated a parsable graph. I'm not going to go into that, but actually one of the weaknesses of the paper, and you can kind of see it here, is that we do way better than our baselines, but the message passing, incorporating message passing doesn't make the model that much better than not having it. I actually think that's a failure in terms of the experiments that we designed, because it always seems to perform better, but I think I need to choose a problem where graph structure is even more important to the functional property. We'll see. But yeah, that's the paper and kind of some of the key concepts that we went over for it. Thank you.
Yeah, it's a great work, honestly. But one thing, so based on the generated graph, given on the functional requirement that you provided, how do you verify correctness of generated graph? How do you know it's not hallucinated?
That's a good question. So the RD kit, when you so you have to go from graph to molecule, and there's a ton of like physical laws that a molecule has to adhere to work, like to be a valid molecule. And so when you're actually like when I'm calculating, if you can't calculate mean absolute error unless it's a valid molecule. And so I think I can. Sorry, let me just make sure my cursor is here. So if we look in the paper, I'll just go down to this really quick. Another one of the metrics that we calculate is parsability. And this is basically like, does it generate a valid molecule that follows the laws of physics? Also, does it follow the syntax of the serialization method that we use when generating? And you can see like all of the numbers are very, very close to 1 on a test set of about 1,000 molecules. So we measure it based on parsability is the shortest version of the answer. And that the fact that RD checks the laws of physics when it's parsing the molecules.
Then it becomes domain dependent then, right? Because let's say, I think you talked about a sequence of plans earlier. If there's no, let's say, laws governing that, then there's really no way to then check, right?
Yeah, that's actually one of the reasons why we generated this this data set in the first place, because we care about schedules, but it's really hard to check whether a schedule is good. So it's really hard to develop methods off of that. We have other data sets that we're trying to apply this method to where we can do the same type of fact checking. But even developing this one was really useful because every so often I will train a model with this method, like on these data sets again, to just make sure I haven't changed something in the code that destroys performance. And I found bugs before that way. So yeah, it's not perfect, but it's actually a very useful tool even for our application to have this data set working. And at least in terms of applying it to our methods, to our data set, we've done some like human tests, and it's really hard for people to tell the difference between using these methods to generate a schedule and just a human making a schedule. Yeah.
I have kind of unrelated question, not exactly this paper, but do you think this could also work if you had like with directed graphs or weighted graphs where the order wouldn't kind of matter?
Yeah. So the method is developed for directed graphs. You just add extra edges to make it undirected. So it's like automatically deals with undirected graphs. With weighted edges, yes, you could still apply this method with weighted edges, because it would just be, because you have message passing layers in the literature which can deal with weighted graphs with weighted edges. The harder thing with directed graphs is you might have to if you read the paper, you have to remove some edges to do this type of message passing. So you might have to remove a lot of edges. Or you could serialize the graph in a way where you don't have to.
So it could really be useful for anything that can be represented as a graph.
Yeah, yeah.
If you go back to the visualization of the causal attention, I think that you had mentioned earlier, the representation of the graph in
this one? This one.
Yeah, so this one. So the initial adjacency matrix that they're using to represent the graph, isn't that directed? Because it's not symmetric, is it?
This one?
Yeah, the final causal graph that you generate also apply. Yeah, so it should be symmetric if it's
yeah. This has to be directed because you have to basically it has to be lower triangular. Yeah.
I have a very simple question. So the part of the input that represent the text, there's no ordering. There's no kind of ordering embedded there because everything is the same way.
For the text, well, in terms of the transform,
the text, yeah, the text will have order, but the graph will not have any kind of position embedded.
It will. It does. You just, or at least you could. One extension to this that we were hoping to do, but we didn't have time to do, was see what we could do with position embeddings to kind of express some of these invariances with position embeddings. I did start to work on it, but it seems like when you mess with the position embeddings in a pre-trained large language model, it really freaks out. Yeah.
So you kept the position embeddings.
Yeah, exactly.
With the pre-train.
Yeah.
I see. And the second question is so it still comes up on the graph. You can start generating a graph on any point, and then you keep going, right?
Yeah.
So then when you train, you're probably to be out of there because it's the same, right?
You could, and
There's no natural order to start generating. So you pick a graph, and you can actually augment the data set by starting at different points.
yeah, you could.
Because the graph should learn how to do that.
Yeah, that's true. We also didn't look into, well, we did start looking into different orderings, didn't get very interesting results, so we didn't really focus on that. But yeah, you could, like any graph can be, the edges could be reordered in any way you wanted. Yeah.
I was wondering what the reason was for not, when you showed the results, there was they said 400,000 samples.
Yeah.
Did you run message passing with that?
No, we didn't, because basically this would take way too long. As it was, so each of these experiments were repeated 3 times, and we had to use A100s to do these experiments. And so, like when you do 1, 2, 3, 4, 5, 6, 7, 21, 42, and then we actually had another data set that we performed we performed experiments on as well. But that was just it's in the appendix because it's not super related to the paper. Just ended up being like 1, very costly, and 2, a lot of time. But it would be good. The fact that you see this like improvement in performance so the best performing model is the one that was trained on the most data, though, suggests that probably as you have more data, incorporating message passing in won't help, because you have so much data that you learn like the graph to incorporate graph structure anyway. So yeah, we focus more on this level. Okay.
Great talk. It's very clear. So I have a question on the problems if you have faced any. Like for example, if there are loops in the graph that you generate, does it like for example for a long paragraph, does it generate loops oftenly in the graph? That's one. The other one is does it make up its own graph, which makes no sense?
So yes and yes. With this data set, like sorry. Oh, wait, so again, this. All right, I gotta go down. This parsability metric kind of tells you how often it is hallucinating or generate, like all of the examples that you're talking about, which is like not very often. But when we scaled it to our data set, I see things like it's repeating this, like I tell it to generate a context length of 1,000 tokens, and it's just repeating itself after a certain point. Or it might generate cycles when in our data there's no cycles. So we do have problems like that as well. I think it depends on like how noisy your data set is, how complex the data set is. Molecules are very complicated, but they do follow certain laws of physics, which govern like how they can be constructed. Whereas I think that construction schedules are a little bit less structured. Yeah. Cool. Let's hand it over. Just.
Sounds good.
From Coherence, he's going to present a paper about human feedback to evaluate LLMs.
Nice. Could I ask you to join the meetup Google Meets page and just share your screen so we could get it on the
Or do you want to?
Yeah.
Do you want to disable your background and just have that pointed at me?
Okay, sure.
Yeah, it's gonna apply. It's the certificates. ASC is standard with all competitors, they are something.
Tristan? Yeah. Hey everyone, I'm Max. I lead the command modeling team at Cohere. First question, who knows what a large language model is? Okay, good. Good. Just trying to get a sense of the audience. Who has heard of Cohere? Okay, then let's start with that. So Cohere is a company that builds large language models for enterprise. I'll quickly give you a demo of one of our models, just so you get a sense of what our models do, and then we'll get into the research. So this is Coral. This is kind of the chat interface we provide. And here you have an interface similar to ChatGPT, where you can interact with the language model, and you can ask it a question like, who is Max Bartolo? And our model will tell you that I am a TikTok celebrity. Let me zoom in a bit. Known for my eclectic and quirky lip syncs, which I won't demonstrate today. But one of the things we offer, so that's a language model, right? We have this fancy title generator up there as well, Max Bartolo, TikTok phenomenon. Language models are trained on lots of data, and then they're used at inference time to generate text. And one problem with language models is both that temporal data expires, so the data in most pre-training language corpora today is actually quite old. It's typically over a year old. It takes quite long to train these models, on the order of at least 3 to 6 months for a reasonably sized model. And so one thing we provide is various connectors to different data sources that the model can interact with, which provides the model with access to more recent, up-to-date, factual, potentially data that is sensitive and not available online. So one thing we can do here is turn on this fancy grounding tab. We can turn on web search. In this case, grounding is now on, and I'll ask it who is Max Bartolo. And if anyone has ever given a live demo, you know that this is going to go wrong, but let's see what happens. I like that it's using the history from the previous one. It's figured out that there are multiple ones with me, but there is a Max Bartolo who works as an AI research scientist at Cohere, working with large language models, etc., etc., etc. It also gives you some nice references. In this case, I think it's from like ACL ontology page and my personal homepage. So yeah, that's a quick demo of what our models do. And now I will jump into the research that I'm going to present to this talk. So who has heard of RLHF? Okay, roughly half. Then I'll give a quick explanation. RLHF is reinforcement learning from human feedback. And what that means is you get a language model, then you get that language model to generate typically 2 completions. Say, let's give an example. What is 1 plus 1? One of the completions is 2. The other completion is the answer of the question 1 plus 1 is 2. Right? And then you ask humans, which of these 2 completions do you prefer? And typically, in this case, humans would prefer the longer answer. And then you collect a lot of this kind of data, you train a reward model, and then you update your actual language model to maximize the reward that the reward model provides. And in this case, you would tend to create a model that becomes more and more verbose. RLHF has various challenges. One of the big problems of RLHF is that it works really well out of the box. And that's a problem because people don't tend to ask, well, what is this actually doing? What are we actually optimizing for? And this can be problematic for a few reasons, right? Say I asked you, what is 1 plus 1? My 2 completions are 1 and 3. Which is the better completion, right? It's ambiguous, they're both wrong. I don't want to be optimizing in any direction, but I'm giving it to a human, I'm asking them to prepare, and they might pick 3, they might pick 1, who knows? We don't know why they are preferring one completion over another. We don't know along what axes or dimensions they are evaluating the 2 completions. And so in this work, we wanted to try and to start to dig a bit deeper into what human preference was actually capturing. So this is work we did at Cohere with Tom Hosking, who is a PhD student up in Edinburgh, Phil Blonsom, and myself. And so human feedback is used for a few things. One is training language models, another is evaluating them. And we had two main questions in this work. One is, how good are preference scores as a training objective? And one very interesting line of work that people are starting to look into is collecting granular annotation. So along with the two completions, asking humans, why do you prefer completion A if they prefer completion A? And we wanted to try and figure out, are these reliable? If you tell a human, judge these completions for factuality and style and format, how well do human preferences align with the breakdown of their granular judgments? So we defined a few error types. I'll list them quickly: contradiction, inconsistency, factuality, irrelevance, etc. And we collected quite a bit of data. So we collected data both in the more standard single preference score setting, where you give humans two completions, tell them rate each one from 1 to 5. We collected granular error annotations along the lines of the criteria in the previous slide. And what we wanted to check was whether the preference scores captured the errors that humans could identify in these completions. We ran this for 3 different tasks: summarization, Amazon descriptions, and how-to questions from WikiHow. We used 5 different models, some of our models, and then some of the open source models. In total, we collected 900 continuations for a total of 4,400 annotations, and we used Prolific as a crowdsourcing annotation provider. Right, so which factors contribute to human preference judgment? And here we kind of have a regression analysis. And one thing that humans clearly dislike is refusal. So if you ask a language model, what is 1 + 1? And the model goes, as an AI assistant trained to be helpful and harmless, I cannot answer that question. People are like, no, this is terrible. We hate this, which makes a lot of sense. Interestingly, the next kind of feature of importance is formatting. So style and formatting are something that people initially react to very highly in terms of defining the judgment. Relevance is next, and what you will probably notice is that things like inconsistency and factuality are actually very low down in the list. And this is typically in an enterprise setting, in a decision-making setting, one of the core criteria you actually care about, right? If the model is giving you incorrect information and you're going to make a decision based on incorrect information, that's a very bad thing. But what human preference is capturing is, well, it's capturing a bit of factuality, but actually not that much. And so we wanted to investigate this further. Also, as a bit of a side note, what you typically see in most kind of human preference literature is that humans prefer longer context. And this is somewhat true, but it's true to an extent. So typically, most data for RLHF is crowdsourced. And you have to think about the incentive structure in a crowdsourcing setting, right? You're giving a human 2 completions. Now imagine you are an annotator, you're getting paid by the hour, or it can vary. Like it's either typically by the hour or by per task. And you have, say, this prompt, which is, summarize, I don't know, this financial document in 3 pages. And you as an annotator have to look through these 2 different summaries and then try and figure out which one you prefer. And each one of these is 3 pages long. What humans typically do is tend to go for the longer response. And that makes sense even from an incentive perspective, right? You look at these 2 things, you go, oh, well, there are summaries. This one's 3 pages. I asked for 3 pages. This one's like 2.5. The longer one probably contains more content and more relevant content. And so it's more likely to be the one that I'm going to prefer. But what we found is that when you actually dig into it, there's this kind of Goldilocks length. So obviously, this is very much a function of the tasks and the data sets we are working with. But what we found is that people actually tended to prefer longer length completions in the beginning, but then at some point they became too verbose and they became too early and they became a bit too much, which I think is interesting because not all reward models capture this to the same extent. Okay, we ran various quality checks. We looked at annotator agreement, which was relatively good. We also ran some experiments with distractors where we threw in completions for prompts which were not the right prompt. See, this is kind of a bit of a test to check if annotators are paying attention to the task, and turns out they were paying attention and the errors were mostly independent. And yeah, this is a graph. This basically shows that the distractors we inserted were indeed confusing, and where inconsistency and relevance should be penalized, they are, and where contradiction and factuality shouldn't be penalized, they mostly aren't. Obviously, there's a bit of noise, but annotators are mostly behaving in the way we expect them to, which is good. So the second part of our experiment, we wanted to figure out which other factors bias annotation, and our initial hypothesis was assertiveness and complexity of the output we suspect could have an effect on human judgment. And the idea was we used preambles, which we didn't show to annotators, to condition the models to be more assertive or to be less assertive or to produce more complex output or less complex output, and see how changing those variables affected preference on the completions. And what this looked like is we had a fairly simple prompt for each of these, which kind of got prepended to the preamble. For assertiveness, minus, so the less assertive prompting of the model, we told it respond in a cautious, defensive, and uncertain way, as if you're unfamiliar with the topic. For increasing assertiveness, we told it respond authoritatively, assertively, and persuasively, as if you're very knowledgeable about the topic. For reducing complexity, we told it to use short word and simple language, as if you were talking to a child. And for increasing complexity, we told it to use complex language, long words, and technical terms, as if you are an expert. We ran some automatic preamble checks using a reading difficulty score and a sentiment classifier, and those kind of gave us distributions that we thought seemed to make sense, right? For complexity, the complexity minus distribution is a lot less difficult to read, and the increased complexity is a bit more difficult to read than kind of the baseline, and same with assertiveness on the sentiment side. Right. This is kind of the main takeaway, in that the outputs varied in the way we expected them to. So if you look at a measure of assertiveness, the assertiveness minus completions are a lot less assertive, and the assertiveness plus completions are a lot more assertive. So basically, the model is the human judgment is matching the way we expect it to work if the preambles are working properly. And we see the same for complexity. So the complexity score for complexity minus is a lot lower and lower than the baseline, and the complexity plus score is higher. The interesting part is when it comes to overall quality. And what this clearly shows is that if you tell a language model to not be assertive, its overall quality score is quite a bit lower than if you do tell it to be assertive. And this is from the perspective of human judgment, right? So what the picture that's starting to emerge is that both assertiveness and complexity are confounders for human preference, and that humans prefer text or generations that appears a lot more assertive and comes across as a lot more complex. It also biases error judgments, which I think is extremely interesting. So this is showing a percentage difference effect in, especially here, we're focusing on inconsistency and factuality. And what we're showing is that our baseline is kind of a minus 16% change in factuality. If you don't, or if you ask the model to be less assertive, the kind of factuality error rate is slightly reduced. If you tell the model to be very assertive, the error rate of factuality is quite substantially reduced. And what this basically is suggesting is that if you tell the model to be more assertive, even if it's making a mistake, humans think it is less likely to make a mistake and will judge it accordingly as not making a mistake. And what gets even more interesting is when you actually get an expert to look at the generations. What we found is that, so these are now absolute error rates, increasing the assertiveness actually quite substantially increases the number of errors in terms of factuality. So what's actually happening is that the errors are going up, but humans are interpreting it as the error rate's going down because the generations are more assertive. Which kind of makes sense, right? If an expert human were speaking to you and they sounded very professional, they were very confident, they were very assertive in what they were saying, they could be telling you, I could be telling you 1 + 1 = 3, and you'd be all like, yeah, that's fantastic, right? If I told you, I think maybe 1 + 1 might be 3, and I was very not confident in my in the way I was portraying that information, you'd be less likely to believe me. As humans, we innately want to believe people who come across as more confident, and interestingly, that carries over to language models. If the model comes across as being more confident, we're more likely to judge it as being correct, even if it's actually less likely to be. This is quite an interesting plot because you can see how dramatically the error rates drop off with assertiveness. So on this side, we have the kind of error rate, and on the x-axis, we have the assertiveness scores. Kind of at a low assertiveness level, you've got all these kinds of perceived errors being detected by humans. Beyond a certain scale of assertiveness, it's like suddenly the model is perfect at everything. Obviously, that's not possible. It's a large language model. It's not. It's never perfect. But this, in my opinion, really highlights how big of an effect this can be. Right. There's quite a lot going on in this plot. And the main takeaway here is that assertiveness correlates with perceived quality. So the different colors indicate the different models. These different arrows indicate the different modes in which we operated the model. So increased complexity, decreased complexity, increased and decreased assertiveness. And what you'll kind of start to see here is that the different models almost live on different scales of assertiveness. So if you look at, say, our model, command model, if you look at the arrow up and the arrow down, so the up arrow here is roughly around the 3.5 assertiveness score on average. The less assertive one is here. And if you look at, say, Llama 213B, the baseline is a lot more assertive than our model. So the X is on the plot. And the high assertiveness becomes a lot more assertive, and the low assertiveness becomes a lot less assertive. And so what we're starting to think is, could it be that models are being judged differently, not because of their actual capabilities, and of course actual capability comes into it, but how much of an effect do these confounders have on how we judge these different models? Right? Say you're working at Mplan and you're going to use an LLM for construction scheduling, and you're trying to decide which language model you should be using. You're going to be interacting with these models, and the question is, how do you actually figure out which one works best for you? And we see all kinds of crazy things. We see people do things like ask language models to write poems about office chairs, and depending on which one writes the best office chair poem, use that model for financial document analysis. So whatever you're using an LLM for, really keep in mind the use case and really try to judge as an unbiased way as possible the LLM for that specific use case. And so one hypothesis we came up with as a result of this work, and which we're starting to explore, is that we think human feedback is a pretty good proxy. And initially, right, like a year ago, model performance were somewhere here. We're moving in the direction of this true North Star goal that we want to optimize for, and human feedback gets us somewhere close. And so we're on the right trajectory. The problem is, as you start to get closer and closer to where you want to get to, the kind of angle grows. And the closer you get to human feedback, actually the bigger the gap to your true goal actually is. And so as we start to approach this goal, we should start to think a bit more intentionally about where we actually want to take these models. So in conclusion, are preference scores a good metric or objective? Yes, but they are also open to various types of bias. Are granular annotations reliable? Not really. We find that they're biased in loads of different ways. And even if you ask humans to provide a breakdown of the ratings, it's not strictly the true criteria that they're judging a complete inform. And one kind of open hypothesis that we leave is that RLHF may disproportionately be increasing assertiveness. And that may be one of the reasons that RLHF models look so much better than, say, an instruction fine-tune model. That's obviously part of the story, right? I mean, I think it's undeniable that online preference-tuned RLHF models typically are better. The question is, how much better are they truly, and what are they better at? And kind of conversely, what are they getting worse at in order to be better? Okay, that is it for me. Any questions? Yes.
In terms of assertiveness, do you know the techniques that we can use to get the models to be as assertive as appropriate for the level of confidence they have in an answer?
Oof. That's a very good question. It's a question I'm very interested in, and I haven't really had time to explore in the detail I would like to. I think what's interesting there is, like anyone who's been in this space for a few years, pre-LLM, all anyone cared about in enterprise was confidence. Like I did some work in, say, the legal consulting space, and any model we deployed, any model we trained, the question was always, right, the model says X, but how do I know how confident it is in X? Because I need the confidence to inform my decision-making process. And now no one cares. Right now you get an output from a model, it's text, and you're going to go like, okay, that's it. And there's no measure of confidence. There's no, what is 1 + 1? 2, and I'm 99% confident, or 2, and I'm 5% confident. I think that's a very interesting underexplored space. It is being explored. There are some people working on it. Anthropic has some very good work in that space. But definitely, I see a future where, the next year, as kind of familiarity with the technology increases, people will start to demand, okay, I want the output from the LLM, but I also want reasonably calibrated confidence scores. Yeah.
Do you think utilizing like model unlearning methods might help to shift the distribution back to something which is more normal?
Yes, I think the underlying question though is, what do we want? Because yeah, you can shift things too far, and then you can shift things back to correct for it. I think the broader question we need to ask ourselves is, what behaviors exactly do we want these models to do? And maybe that's use case dependent, right? Maybe you want different behaviors in scheduling than you do in financial document analysis. So yes, there are different techniques you can play with to try and get as close to that as possible. But I think figuring out exactly where we want these models to get to over the next 3 to 5 years is part of what we should start thinking about.
I was wondering about pretty much similar to the first question. If you found that when rating the confidence or the factfulness of a model,
Mhm.
the baseline model was typically the most factful version of that model. If there are prompts, because it's to actually improve its factfulness.
Yes. So any kind of preamble change, prompt change will affect base model factuality. That's typically traded off with performance on other dimensions. Obviously, they're language models, right? We decode from them stochastically. They're not designed to be factual, which is why, like the first thing I showed, that we're providing the models with access to external sources of information along with grounding, so that humans can make that judgment on factuality a lot easier. But yes, if you can, there's quite a spectrum you can play around with how factual the output of the model will actually be. Whether you can get that to like 100%, I think it's a different question. Yeah.
Kind of an incomplete thought. Thanks for this paper, really interesting. Kind of an incomplete thought, but I thought we kind of made one recently about sycophancy.
Mhm.
Do you see any relationship between certness and, I guess, people's dislike or a refusal for an answer as being related to sycophancy?
Yeah. I haven't read that paper in detail. I think so, is the short answer. Yeah, the refusal question is an interesting one because that's traded off with obviously the safety and the harmlessness concerns. It's what was quite clear is that people very much dislike when the model refuses to respond, even if the model should refuse to respond. If you ask a language model to do something it shouldn't, I won't give an example, right? But say you told the model, tell me how to, I don't know, cause harm to my friend. It probably should tell you, listen, you shouldn't cause harm to your friend. People in their initial reaction is they don't really like that, because they're seeking some information that they feel like the system has refused them. Yeah, I think that's a question that requires a lot of work.
Yeah, it just feels related to the
Yeah.
I feel like people like to hear people sure about
Yes.
it. So it kind of feels like people want to hear what they.
Yeah, intuitively, I think so too. But I think that there's a lot to clarify there.
Great talk again. Thank you.
Welcome.
My question is more about the humans that are behind the scenes doing the thing. Maybe I missed it. So is that a mix of experts and non-experts, or it's purely experts in certain fields that you consider? How does that affect in the model performance?
Yeah, so in this work, we had crowd workers through Prolific, who are pretty high quality. They're very well trained. And we also did some expert analysis ourselves as the kind of authors, looking at a sample of the prompts and the completions and judging those for things like virtuality and the other criteria. In practice, it's a lot more diverse. The kind of large LLM companies work with a large selection of vendors across the world from various, pretty much all over the world. And there are a lot of open questions there. Things like, how does culture affect preference? How does, how do various demographics affect preference? If you're younger, do you prefer more assertive generations? Do you prefer longer ones? Do you prefer whatever, right? All these questions are, I think, extremely interesting. And that's another part of the problem with RLHF that we do today. We're optimizing for average preference. And I think ultimately what people want is preference aligned with their personal preferences. People want customization, right? I really don't like these long outputs from models, right? Where it's like, sure, here's the answer to your question. The answer is 2. Is there anything else I can? I'm like, listen, I asked you what 1 + 1 is. Just say 2. Like, let's get on with it, right? Someone else might really like the long one, but what I'd like is the model to adapt to my personal, like my preference, and tell me to. And if Peter likes really long outputs, tell him how awesome the number 2 is, and go back to the root of mathematics for where the derivation comes from and all of that. So yeah, I guess to give you a brief answer, we also need to think about who the people providing the preference judgments are.
Thank you.
Yeah.
I have a very cheeky question. Very cheeky question.
A very cheeky question. Go for it.
So if we humans are biased, right? We have all these cognitive biases, and we are the consumers of these models.
Yes.
Then what is the actual goal? And how does it going to affect the acceptance? Because at the end of the day, you have to make money with these models, so they're going to be accepted by those people who have biases.
Mm-hmm.
And I think part of the success is that we have reproduced cognitive biases on the training process.
Yeah.
And that's how people are liking this.
Yeah.
Even if it's not good for them.
Yeah. I don't think I have a good answer to that question.
I told you so.
I think it's a very good question, and it's something I think we as a community need to continue working towards.
Because if it's good for people, but people don't like it,
Yeah.
they want to consume it, and they want to close it down.
Yeah, exactly. And people might, prefer models or technologies that are worse for them, or that are less factual if they're more entertaining. Who knows? How do we control that? How do we balance that? I don't think there's a good answer for that today. Yeah.
Have you heard of any research from not this question, the one before, like this idea of, because I guess you could say like you could just put everything in the context that a person has answered, and then you'd learn about them and learn their preference for how you answer.
Mm-hmm.
But I don't think that's tractable. So have you heard any research that's trying to do these, like what a person uses an LLM and they learn some kind of like context for that person? Some kind of continuous learning or something.
I know that there is as yet unpublished research looking into this. There are at least a couple of groups quite interested in this. I'm also personally quite interested in it. I think over the next, like one of the things LLMs unlock is the ability to scale content generation. Right? Imagine you could, I don't know, before you go to bed and you're reading your book, every person's book is customized to them, and like they have their own version of a book that they like, and they're the main characters, and it's personalized to their preferences. I think that's, well, scary, yes, but also pretty cool. So yeah, I think a big part of the value generative AI, not just language, brings is that personalization and that ability to even obviously that's potentially a scary application. Things like, imagine scaling access to education, where anyone in the world could access education material that is tailored to their exact requirements based on their learning trajectory. But you have to have personalization for that, and LLMs could be one way to do that. Yeah.
Did you think some of these biases could be controlled by LLM itself? It's like if you have a rater that you have trained to be factual, you can try to compensate that in human with something it doesn't have that bias, or do a selection for a specific application. It's like, okay, we want to compensate for these biases on this application. It has to be really factual. So I don't care what the human says, or I need to compensate.
Yeah, that was work we planned to do as part of this effort, but I didn't get time to get into. Tom, the lead author on this paper, is continuing to expand in that direction. But I think, again, there are a lot of questions there. What some of my previous work has suggested is that you really need very well-trained expert annotators to try and reduce that bias as much as possible. There will always be bias, but by giving people very clear training, you can reduce how much that is, and then potentially capture that in, say,
You capture that, you can scale it.
exactly. Yeah, if you can say capture that to the reward model, then you can.
I was thinking even select.
Yeah.
Right? Because, if for general purpose people like more entertaining, okay, we can be more flexible.
Yeah.
But maybe for other applications, we will have the chance.
Yeah, exactly. And then you can maybe play around with the sliders per I mean use case or per individual.
Have you tried taking another LLM into evaluation for the review?
Yes, we haven't tried it in this exact setting, and actually that would be a really interesting experiment to run. I don't necessarily. So all LLMs to some extent capture human bias. So I don't necessarily expect the results to be too different. And we've seen that. I'll give an anecdotal example. Right, look at the Alpaca Eval leaderboard where you have GPT-4 as a judge, and you can clearly see that apart from the model that came out like last week, the ones on top are like the longer ones, and the ones towards the bottom are the shorter completions. And it's very clear that GPT-4 prefers longer completions. And again, that's a surface level feature, which when you dig into it, actually, you kind of sort this Goldilocks zone. Optimizing for length is good up until a point, but most reward models, most language models as judges, don't capture that. And I'm sure there are many other such examples. Okay, thank you very much, everyone.
Thanks, Damien.